part in several different forms, or several different random networks. So, and I do it in a layered manner. So the first one I have is the mothernet, well, obvious name. So every node is taking part of that. And the first, the next layer I do is actually the application subnets. So each application, for instance, if you use my programming library, then and you do a chat application, you do a gaming application, you do an internet telephone game or such. Each of those should have their own random network, their own application subnets, where they do their stuff. Because the mothernet can do some things better. Agreeing about time, for instance, the more nodes you have, the more secure that network becomes. Also, bootstrapping, finding the network, it helps. The more nodes there are, the more likely there are nodes that are more often with the same IP number. For instance, when you start a new network, if there's only 10 nodes in that network the first weeks, there will be moments when all of them are offline. And if all of them go offline the next day with new IP numbers, they will never find each other. But if you then kind of parasite off an old mothernet where there are many other applications and big applications with many users, then you still have somewhere you can bootstrap and create your little application subnet, and the next time the other one goes into the mothernet, you will find the application subnet and you're fine. So that's one layer. You should also have public subnets, because sometimes two applications want to cooperate about the same thing, doing the same thing. So it might be two chat applications using the same protocol. And they need perhaps one application subnet for one of them to count the number of users for that version of the software or that software. But they of course take part in one where they actually do the chat room stuff. Yeah. The next layer I use is the application. That's the same yellow one as the other one. That's for one application. Underneath them I have many service subnets. One can be a chat room. Each chat room has their own form. One can be a username. So my name, David, could be its own subnet. So when you want to connect with my computer, you will in the same system search for my name. The same search that you use to find the chat room is the same problem, to find at least one of the nodes with that name and connect to them. And I do one extra thing here. I put the DHT or the search system, I put them in their own service subnet. Because DHTs, for those of you that don't know what it is yet, don't bother, we'll explain that later. DHTs is ongoing research. We don't have the perfect DHT yet. There comes a new one every third year that's better. Back then it was a new one every second month. So I plug the DHT into one of the service subnets, and then you can actually, when there comes a new better one with a new version of the software, you can create a new subnet with a new name. And that new version of software can work both in the old and new DHT. And then when some versions later, you can perhaps start working in that old DHT. So you can be future compatible in that. You can plug in new functions as service subnets in the application. So every new function, not every, but some of course you can just extend the protocol in a way that doesn't crash the old nodes, because nodes should accept that you have some extra data. But some things, if it's not compatible enough, you put it in a service subnet and don't bother about the old nodes. For instance, DHT searches are all DHT databases I know have distributed hash tables can be crashed. I haven't seen one I can't crash yet, or at least disturb in a different manner. While broadcast search, that also is a bit more robust, but clumsy in other ways. So I would like it ideal to have both in my network. So you use the DHT because it's nice, you can do much of cool stuff in that, but when it behaves badly, you use the broadcast search. So the broadcast search sometimes is actually better than the DHT for some things.
We're going to be talking later about the different use cases.
Yeah, and I'll also explain how to do it. We'll go into that. So this is the two levels layers really. Mothernet, three nodes, application subnet, and service subnet. That means nodes that are broadcasting something within somewhere, they only broadcast it to nodes that actually want that traffic. Let's see what okay. Yeah. For instance, in a chat room, the address of the chat room isn't simply the name, it's the hash of the name. Everything when we store it in a database or in peer-to-peer systems or as an address, we'll always hash the name to get the address, because if you hash it, you spread the name out in the namespace. We also, let's see, if it's a chat room that's not public, that needs a password, you simply take the name and the password and hash that together. So the actual name is the hash of the name and the password. That means other nodes in the application that you see there is a chat room, but they don't know the name of it. And even if they can figure out the name, it might be, for instance, it might be engine yard. But if they don't know the password, they can't figure out the hash sum of that. Then they can't know which of all the thousands of chat rooms they see is the engine yard chat rooms. They can't even find which nodes are the engine yard nodes.
But they're still visible though, aren't they?
Yeah, as a group of nodes that are obviously cooperating, because they're announcing their hash sum up here. So everyone can know there's, for instance, 1,000 nodes in that chat room.
So you could go sniffing if you wanted to.
What if they're using cryptic connections?
Invisible software.
So those nodes, all the connections should of course be encrypted. Then that's what almost goes like without saying. So if you start listening to those nodes, you don't know what they chat about, you still know the engine of the other nodes. Or if you know the IP numbers, you can figure out where they come from, very quickly realize. Yeah, all these nodes are from that company, of course, so I do more stuff. We'll go into that. I use some added hash caching method and stuff like that to make it harder to do some stuff that, but we'll get into that later. Yeah?
So if there were just a few private chat rooms, I could try to put an attack to just all the ones that are encrypted. And
yeah, but you won't know which they are, because all the chat rooms are, okay, if some chat rooms are published, you know they are, because you can take the name, hash them and say, those nodes are in that node. But all those that you don't know the name from look the same. So you don't know if they have the password, you just know that I don't know what this hash sum means, I don't know if it's a public chat room or not public chat room. Yeah.
Okay, so there'd have to be a lot of them,
Yeah.
so that it would take too many resources to attack all of those.
Yes.
Okay.
Yes, of course, if it's when an app was small, you can always do DDoS, all the nodes in
Obscure, just have a lot of golden chat rooms. Find the name of that.
Alright, okay, that's contact. Let's see what comes next. Oh, protocol search. Oh, sorry. Pause. Went too fast. To do this lookup from mothernet to application subnet or from application subnet to service subnet, that's a lookup. That's actually kind of a database thing. So we need some kind of routing overlay of database for that. We could, of course, use a distributed hashing table for that or a broadcast search for that. But both those approaches are wrong. There's a better way. We can use part of the DHT technology for that. We can use only the routing overlay. Yeah, okay. We'll look at it more later, but I can give you the basics. On one network, like the mothernet, we can announce a number of subnets, but we can't announce one in each slot. But if it gets too many slots, it gets big. We can have one app will have 1 million slots that we route independently. So what we do is we announce, for instance, 16 slots, and if we get more than 16 application subnets, we make a new layer underneath that with 16 slots and 16 slots and 16 slots. So that's kind of the routing overlay for those who know about those. But we don't store data in the nodes now with this DHT. Instead, we actually insert the node. So it's like a distributed hashing table, but what you reach isn't a node that tells you about something else. You actually reach the node you want to talk with. And that makes this routing overlay robust, because you can't insert false data in that sense, because the node that you reach will actually be the node, and if you can't connect it correctly, it doesn't have the encryption key and stuff like that, you notice it's a false node and pick someone else for that. But we'll look more at that later also. So I use subnets under subnets to get this routing overlay. So it's actually many layers between here, but that's just a technical thing. Yeah. So we'll get more into that. broadcast search. That's the old Gnutella style broadcast search. Okay. Basically, you connect all the nodes in a random network. Let's say 5 links to each node as usual. When you search for something, you just put together your search message as a little package, and you send it to all your neighbors, and they send it on. And with the hop counter, when it gets too far, nodes will start. So you accept a certain number of incoming searches per minute, and send some of them along. But not, you don't flood your neighbors, you just send a limited number per minute or per second to neighbors. And that way, usually you can search, say, the 1,000 closest nodes. That's a normal number. It depends, of course, if there's only one node searching out of the whole million, it can search. That message will reach all nodes and will actually search the entire network. But usually everyone is searching every now and then. So, and a fairly normal number is that you have a search horizon of 1,000 nodes. And that might be a little, but we then have methods to improve that. For instance, what we can do is that, for instance, my node here, it can collect data about its neighbors. It can actually get all the data on neighbors, all the file names it has. So when my node gets a question, you don't need to broadcast it to the next node level. It can actually respond immediately. That means we can usually reach about 10,000 nodes in a normal case. There's also something called a bloom filter. How many here have heard about bloom filters? Yeah. It's a way where we kind of take a hash sum. It's a kind of hash sum actually from all the neighbors that tells us. So when we can compare an incoming question with this hash sum and see if it's likely that my neighbor has an answer. It doesn't prove that neighbor has an answer, but it can prove that neighbor doesn't have an answer. So sometimes we'll get false matches, but that means we know if it's worth the trouble to broadcast it one more step. And that also adds about 10 times more. So we can know about 10 neighbors. So that means we also can get the search horizon of 10,000 nodes approximately. But then there it stops. But there is one more technology. You can use something like mini groups.
Sorry, what is that?
Mini groups.
Mini groups.
Yeah, that's my only mention. Yes. That's my only. And I don't know why I haven't seen anything published about that. No one else seems to have come up with that. Because you can, it's kind of like a super node thing. You connect to neighbors and get their data. But in this case, I connect all the nodes in groups of say 1,000 nodes. And within this group, I do gossiping. Actually, the modern kind of gossiping. I broadcast everything about everyone in a smart manner, in an efficient manner. So in a normal order.
Like order takes for the dialogue.
I don't think we know.
So the Gothberg, eventually all of the nodes in that mini group know that all of the nodes in that mini group.
Okay, but that's just kind of possible. But it's clear. They use the ring.
Yeah.
And actually, you can do it. Okay, we can do it in the ring example. You connect all nodes in the ring. And that's actually a simpler example. That's where I started before I invented mini groups. So I connect all nodes in a ring, and you tell all your neighbors about what data they have. Like you send it along 100 nodes in that direction and 100 nodes in that direction. And when someone gets a search request, it can actually respond for all of its neighbors. And then you can actually, with that technology, you can reach a search horizon of about 1 million nodes. Because that's more efficient than using supernodes. I'll get into the details later on when I show you these algorithms. But using the ring was slightly stupid, I found, because handling the ring is actually complicated. It's too well structured. So instead, what I finally did was that I collect nodes in groups of 1,000 nodes. So I have many such groups. Each group, everyone knows about everyone within this group. Exactly the size for that can actually be calibrated in real time, because it depends on how much data the nodes have. Because if each node is sharing too much data, then you need smaller groups because you can't handle so much information about neighbors. So the size of these groups have to be more proper for what amount of data they're sharing. But that means that all of these 1,000 nodes can respond to their neighbors. When you use supernodes, usually the neighbors, only the supernodes answer. The nodes that are connected to supernode are passive, so they don't do work. And that's stupid. You have passive nodes that can contribute. So basically you have the ring or all of these groups. That's a small world network, and then you have a second small world network where you do the searches. So that means that when your search question goes out of the random network, each node it reaches takes part in another mini group. So each of these nodes represent 1,000 nodes. So you ask 1,000 nodes, and they represent 1,000 nodes each, using million.